Physicist, or what are you? No one's volunteering? Chemistry, physics, or?
Graduate students.
Yeah, okay.
Yes.
My name's Alex Monchak. I'm in the engineering management program.
Engineering, oh no.
University of Chicago, with the goal of getting back to work with JSCA. So
There was constant warfare between engineers and scientists on this mission. It was interesting. Anyway,
was what?
There was constant warfare between engineers and scientists on this mission, and
Well, we're trying to encourage more of a collaborative effort because we find that the scientists usually, from our engineering perspective, usually add value, much value.
Anyway, long story, maybe I'll go on. Okay, this is I'm going to talk about this mission, which was primarily to visit a comet and return samples to Earth. Okay, it was the first such mission, actually the first sample return mission since the Luna Russian mission, Soviet missions, and the Apollo missions back in the 60s and 70s. So it's been 30 years since the last sample return mission, and so a lot of the struggle for this mission was in learning how to do a sample return mission. A lot of things have been forgotten, had to be refought over basically. And amazingly, once samples came back, over 200 scientists worldwide worked on analysis of the samples over the first 6 months they were back on Earth. So it was an amazingly large effort on behalf of many, many scientists, I think 5 comets. So briefly, comets, okay, why are they important? We think that our solar system was born from a cloud of dust and gas like this one, which for some reason began to collapse, and little knots like this began to form. And magically, one of these knots basically collapsed down into a revolving disk of dust and gas, and material moved in, and as you probably know better than I do, material gradually formed a nucleus which was dense enough, large enough, and hot enough to burn as a star. And around this object were balls of dust and gas which slowly condensed and created to form planets. Okay, but not all the stuff around orbiting around this star became a planet. Okay, lots of material ended up as small rocky or icy objects, which today are called asteroids or comets or Kuiper belt objects. Okay. And the step between here, this last step where you have rotating dust and gas, and this step here where you have these planets, these nice little racetracks around the star, it's very complicated. No one understands it very well yet. Okay, and we think that during this period here, when the large planets were forming fairly far from the sun, they were sweeping up small rocky objects, incorporating them into themselves. But in some cases, material would pass close by these evolving giant planets, and instead of being incorporated into them, would be swung out into new orbits. Okay. Sometimes material would be pushed inward towards the sun, but sometimes outward. With the grand result being out here beyond the planets, there's a large disk of objects now called Kuiper belt objects. So here in this diagram here, the planets are in here, the orbit's here, and this is Pluto's orbit, which was a planet. I made this slide. Now it's not a planet. It may one day be a planet again. Okay. Now here beyond the giant planets are millions to billions of icy rocky objects called Kuiper belt objects, okay, which is probably the last bit of this protoplanetary cloud of dust and gas, material that's largely where it was in place for billions of years. But out beyond the Kuiper belt, now this whole little rectangle here is squeezed down into this little light blue rectangle here. Way out beyond the Kuiper belt, there are icy rocky objects out still orbiting the sun, still belonging to our solar system. And they're basically orbiting in a giant basketball. Okay, it's like a giant hollow sphere. These are objects which we believe were perturbed outward from here by the formation of the giant planets and pushed out almost to the edge of the solar system, not out of the solar system, but to the very edge. They slowed down, came to rest, and they're still orbiting way, way out here. They still belong to our solar system, but they actually were formed in here, and they were pushed out here by the formation of the giant planets. And this has been called the Oort cloud. It hasn't been seen. The evidence for this is in the existence of long period comets, which come in at any direction. They come from any direction. Okay, you have two kinds of comets. You have comets which primarily are orbiting in the plane of the solar system and appear to originate out here in the Kuiper belt. Okay, and then those have shorter periods and they're elliptical orbits and they're hundreds of years or less in period over the period. Then there are guys which appear to originate out here in this cloud called the Oort cloud. These comets have much longer periods, much longer than hundreds of years, up to millions of years sometimes perhaps. And they come in from any possible direction, which suggests that this cloud, like I say, is really a sphere around our solar system. Okay. So oddly enough, the things here that are further from the sun probably have been more active in the past, formed in here and were pushed out billions of years, back when the giant planets were still forming. Okay. So the point here is that these comets, whether they're from the Oort cloud now or the Kuiper belt, are really leftovers from the formation of the planets and the sun. And if we can grab one and bring it back in the lab, we can discover a lot about what the raw materials are like from which the planets were formed. And we also think that comets provided the Earth and the extraterrestrial planets with most or all of the water that's there today. It's debatable. And a large amount, maybe most or all of the organics. So material in your body perhaps all came from objects that formed out here. Okay. Questions or comments? Okay, let's move on. I might say that lately, the last couple of years, has been kind of reevaluation of this model. And people who look at the formation of giant planets, there's some evidence that suggests that as the giant planets formed, they moved around. And that perhaps Jupiter moved in closer to the sun after it formed. And the other giant planets moved outward, away from the sun after they formed. And I'll go into the evidence for that. But if that happened, the implication is that as that happened, they perturbed the orbits of the innermost Kuiper belt objects and sent a lot of these comets in all kinds of different directions, including into the inner solar system, where they could be today as asteroids. So it's possible that in the past people kind of differentiate between asteroids and comets. Asteroids, drier, no atmosphere, perhaps lower in organics and water. Comets, more pristine, more primitive, colder, perhaps a lot of water ice, more than in the asteroids, perhaps more organics. Okay, but perhaps they're really the same thing, just sort of mixed up. And perhaps a lot of the things to think of as asteroids today are really just the nuclei of dead comets that were pushed in the inner solar system billions of years ago. That's the last couple of years. There's evidence for that from this mission, actually. Let's scoot on here. This mission was made possible by a couple of things. Okay, turns out that you want to go visit a comet, get samples, bring it back to Earth. Okay, it's very hard to do that for a cost that NASA will bear. Okay, at the time we proposed the mission, the cap on the mission was about $200 million. We couldn't spend more than that. For that much money, you can't go to any comet. You can't, like Halley's Comet, you can't land there. You can't grab a sample and come back. That's a $1 billion plus mission. Okay. Actually, for Halley's Comet, it's several billions of dollars probably. Okay. For $200 million, sounds like a lot of money, right? And it is. But for that much money, all you can afford to do is kind of go by a comet that's conveniently located near the Earth. You just sort of go by it, try to capture some dust from the cloud of dust and gas that's around it, and bring it back. That's all we could do. Turned out there's only one comet we could easily visit, and it's this one here, called Vil 2. And Vil 2 is an interesting comet. Prior to 1974, it had this orbit. Here's the orbit of the Earth, this little white circle here. Here's the Sun. Here's Jupiter, Saturn, and Uranus. Okay. So prior to 74, when I was in high school, okay, it was orbiting out here in this yellow orbit, out in the Kuiper belt, in to where Jupiter is, in Albion. Okay. But in 74, it had a very close approach by Jupiter, so close that it was swung into a new orbit. It almost collided with Jupiter. Okay. And its new orbit is this guy in red here. Now it's orbiting out to Jupiter and in almost to Earth. So this is a fairly fresh comet in the inner solar system. Fairly easy to visit, relatively so. Okay. And so this is one we chose. Okay. Vil 2. Not a famous comet, but the only one we can really easily visit. And again, instead of landing, what we did was we flew by with a spacecraft, opened up a tennis racket. This is the return sample canister for Stardust. Let's do that.
Just say no and
And this is the collector right here. And it's interesting. It looks giant in this picture. Actually, this collector here is about this big. About tennis racket size collector. It's got 100 odd pieces of silica aerogel, really low density material composed of silica, sitting as a window glass. Okay, only it's like foam. Okay, it's solid foam. Extremely low density. Okay, populating this tennis racket. And the idea was that as the spacecraft went by the comet, it opened up, fold this arm, open up this tray and wave it around, and the dust from the comet in the nucleus would smash into the aerogel and come to rest inside the aerogel, and it would fold up back to Earth. Okay, we couldn't just use any kind of collecting mechanism because the comet was traveling much faster than the spacecraft. When I said the spacecraft passes a comet, it's actually kind of a misnomer. Actually, the comet flew by the spacecraft. It was traveling so fast, it actually passed by the spacecraft at a relative velocity of over 6 kilometers per second. That's 10 times as fast as a rifle bullet. So you got the spacecraft, the comet goes like this, right by it, okay? Dust from the comet slams into the spacecraft. It's like being shot by a very, very fast rifle. So the question is, how do you collect dust without destroying it or the spacecraft at that really high velocity? The solution was to put shields around the spacecraft, and this tennis racket waves above the shields, and this aerogel basically acts like a thick atmosphere. Particles crash into the aerogel and slow down inside the aerogel and are captured inside. And this worked. I mean, amazingly. It sounds very complicated. It was fairly simple and actually worked amazingly. So with me here talking about today, we launched in 1999, a 7-year mission, came back in 2006, 2 years ago, launched that tiny little Delta rocket. I think it cost $50 million for the rocket. That's a quarter of the cost of the mission just for the rocket. But it launched okay. This is the plan. This is the plan for the mission. Here's the sun. This diagram, the orbits are in the same place. Okay, here's the Earth's orbit here. Here's the comet's orbit here. It's kind of a sun-centered coordinate system. So the spacecraft launched in '99. Went around the sun 3 times. First 2 times, basically getting oriented to go up and out of the plane of the solar system. Third orbit goes out, intersects the comet, January 2nd, 2004. We didn't hit the comet, that was good news, right? And then returned to Earth 2 years ago in 2006. I'll show this diagram later on, but this is the plan of the mission. So 7-year mission, kind of a long time to wait. Picture of the spacecraft. It was actually would have fit on this stage. It's quite a small spacecraft. Big solar panels. This is the size of the tennis racket, about so big. These are the panels that protected the spacecraft from the comet dust, and they worked. Basically, the comet's actually passing by the spacecraft like this. And this side of the tray then is getting smashed with grains of dust from the comet. For a second, take a look at this picture. These are solar panels that folded out, okay? And we were worried about the possibility of dust grains smashing on the edge of these shields and spraying material from the shields onto the tray. That happened in a couple of cases, okay? Or hitting the solar panel, these are silica solar panels, and splashing up onto the tray as well. That shouldn't have happened from the comet because the dust is traveling into the front where these shields are. But occasionally you'll get stray dust grains orbiting the sun, which come from any direction, could come down and splash into one of these solar panels and ricochet off onto the tray, and we saw that as well, later on. After it passed by the comet, folded up, and all that came back to Earth was this little capsule right here. Okay, so here's the comet as it passed by the nucleus. It has kind of the shape of a hamburger with the bite taken out of it. Okay, so I'll go back in a second here. We'll go back in a second. So this is 5 by 7 kilometers across. So not very big. You can walk around it in a day easily. Okay, it's got a very, very odd surface texture, as you will. Okay. It turns out that all the comets we have pictures of look totally different. It's amazing. All the nuclei look very, very different. This one's the weirdest one of all. It's got these huge footprints across it. Lots of round things look like impact craters. And these little deals look like horns and little spires sticking up like this. like a spiky, like a porcupine almost. Very, very strange surface morphology. So this is a very active geologic history which no one suspected it could have. We'll come back to that in a second. Okay, put your glasses on for a second if you will. Can you see that, or? There's a right left eye thing, right? I mean, so make sure you get it right. I can't see it, but you should be seeing these huge depressions here, which most of us believe are. So when you see depressions like this, you think impact craters, okay? But the problem is that comets should have been far enough from the sun and other objects. They shouldn't have been heavily cratered by objects. Okay, they shouldn't have had a lot of things smacking into them. Perhaps when they formed, they did, right? But since then, there should have been a lot of things hitting into them. And so if these really are impact craters, you know, why do they have so many of them? That's a big mystery. These guys here, we believe, are actually features that are formed by gas, heat getting in to the inside, ices vaporizing, things like CO and CO2, other gases vaporizing, spewing out, degassing. It makes a big cavity inside which collapses under the force of gravity here and makes these depressions. Okay, so these are perhaps ablation features. Is this all working? Does this all work for you as 3D or no? Is it working?
Yeah.
I mean, just a second here. It varies from room to room, so. Oh yeah, okay. The cool thing are these little spires, call them spires up here. These are 100 meters high, 300 feet. Okay, and they come to a point. It's amazing. And here, this is actually a large wall of ice and dust. It's actually greater than 90 degrees. It's actually overhang, like you'd see on a ski slope, ready to avalanche down. And it's here as well. Okay, so here's one of these basins. Again, I think these are formed from material ablating from inside. Creates a large internal cavity which collapses down, makes this big depression. But no one really knows yet. Not like anything else you see in any interplanetary body. It's a totally weird thing. I think that's called a right foot. And you see this feature here. These are all over the place. They're basically circular depressions, but very, very shallow. It turns out that if you have an impact into a multi-layer material, like dust covering hard material, you get an impact crater like this. Well, if these really are impact craters, it's a mystery why there are so many of them on this surface. No other comet shows being like this. There's lots of them here. And these little spines, these spires we're talking about are like here and here, here, they're all over the place. Okay, and this is hard to see, but here on this image here, you see these little lines. Maybe this isn't very obvious, but this is 3 blocks of ice, 1, 2, 3, and they're tilting like this. This piece here is lower than this piece. This piece is dropped down into a depression. So my interpretation of this is that material has been ablating out the inside. There's a large cavity below here. These pieces are basically falling into it. So it's one of these big depressions being created. So you have basically normal faulting on a comet. So as low as gravity is here, it's high enough to actually cause landslides and things. Landslides. Okay. This is a kind of a cool 3D image that shows these gas and dust jets coming out of the nucleus. And we thought we'd see a few of these jets of dust and gas, and we saw dozens of them. Okay. And this one here appears to come out right out of the center of this big depression here. It's consistent with these depressions being created by ablation from inside. Okay. There's a weird thing. Most people thought that comets would lose material from the surface only. This guy is losing material from the inside. And why it's heating up on the inside is a big mystery still. No, it's a mystery. And if you look at, there was actually a detector on the spacecraft which told us when the impacts were hitting the collector. And rather than seeing an even number of impacts peaking at the closest approach to the comet and then trailing off again, we saw where all the dust hit the spacecraft at three times, 3 discrete times. Which means that the spacecraft actually sampled just 3 areas. And as you flew through a jet, we'd get a bunch of dust hitting the spacecraft, then nothing for minutes. then another burst hitting it, nothing again, and then another burst hitting it as well. Which means these jets are highly collimated. We passed, the closest approach was 230 kilometers to the comet. Even that far away, these jets of dust and gas were very highly collimated. Like little pencils coming out. It's amazing. Anyway, I'll go on. Okay, this just shows a kind of a rogues gallery of the best images of 4 comets. Temple 1, this is the one that the washing machine hit for deep impact, right? Down here is where it hit. Borrelli looks like a chicken dumpster. Halley and Zil 2. These are all the same scale, roughly. And they're all totally different looking objects. I mean, very, very strange. Like moons of Jupiter, they all look different. Okay. You can see how smooth Temple 1 is, more like we thought we'd see our comet. This guy just totally pockmarked with dirt. And it's not clear why that is. You may never know. It's pretty cool. So comets have had wide different histories. They aren't all the same things, apparently. Okay, re-entry. If you're wondering what this is, the spacecraft re-entering. It re-entered very fast into the atmosphere. 3 a.m. in Utah. Everyone would know that's what it looks like. Got a little movie showing it. Get out of this.
You can just click on the bottom on the movies at the bottom.
Oh, yeah. Well, that's the wrong one, though. I need to get to. It isn't open. So I should get out of this thing. Okay, there we go. So here's a movie of the re-entry. So it's at night. It's a very cold night in Utah. You know, there are clouds. Actually, it was snowing. And here it is. So this object is this big, coming in the atmosphere, trying very, very fast. Much brighter than we thought it would be. It's amazing, actually. It's a treat. And it's actually coming directly at us. It's weird. It looks like it's going away from us. It's actually coming directly at us. It's a weird perspective deal. That was exciting to see. Actually worked. Well, it came down in a large military reservation where they test cruise missiles. And all across the surface there are unexploded cruise missiles. There's a chance we actually could hit one of these when it hit the ground. And also, to go recover it, we had to have all kinds of practice in what to do in case you see something strange. And for the practice runs, they take us in a bus out to some place and then drop us off, we'd walk out, practice recovering it, and you'd see a piece of ordnance like every 10 feet. You know, a rocket here, or a landmine here, or a piece of something over here, or, you know, a cluster bomb over here. It was amazing. It's a really dangerous place. And if it landed over here, this is the world's largest kind of weapons depot. So if it landed there, you couldn't get it. There's a large fenced-off area. If it went in there, you couldn't get it. You wouldn't be able to get it. So we were kind of worried it would go in there, but it didn't. Luckily. Okay, landed. Here's the spacecraft. We carried back, opened up. Just a mile or so away at JSC, opened it up in the clean room there. So here's the collector tray. Again, it's over this big. And here are severe gel. Here's the impacts. Okay. This is the biggest one. Here. This you can feature a little finger into. These cells are 4 centimeters long. So a couple inches long. These are big ones. There's one. These are smaller ones, impacts. Each cell has the average cell has a few largish ones like this, and hundreds of very, very small ones. And about every 5th or 6th cell has a big one like this, or like this. We actually can see some dust in the impact feature. Well, the material entered, kind of exploded, and was deposited along the impact feature in the air gel. And on the side, it looks like this. These are the tracks turned on side. So they enter off on the left here. Part comes in. Sometimes they break apart. The material along inside this track bulb, and then grains are scattered along the length of the track. And scales here vary, but each this is about as wide as a human hair here. These are human hair size objects. Grains at the ends are 40 micrometers in size and smaller. So at this scale, a human hair is the size of the screen, basically, in diameter. But human hair is like this. Very small objects. Up here you can see people have pulled out grains from along this track, and these are other pictures of the grains are pulled out. So the model is the grain is an aggregate of little particles that are nanometers in size. They enter, break apart, and the largest grains are say a micrometer in size and larger, travel down and get deposited along these tracks. Here's one here.
Mike, for the, you photograph the cells before takeoff?
No, we forgot. Yeah, of course. I mean,
Well,
we
I
did
mean,
all kinds of stuff. We have like thousands of pictures. They did density measurements, infrared measurements, all this stuff for the cells.
Okay, so,
If you're interested in big valid data at JSC,
yeah, I'm just wondering, are there any anomalies just because of the entry?
not in the air gel.
Really?
Yeah, so the air gel was inside of the sample return capsule. It wasn't hermetically sealed. Air got in, but we haven't seen anything in the air gel from the ground. There's manufacturing defects, like little grains of junk inside the air gel that was just when they manufactured it. They didn't clean out materials as well as they could have. Things like that.
No tracks?
No, nothing. Yeah. We worried we'd see all kinds of outgassing from the spacecraft. We didn't. Very, very tiny amounts. Basically, the idea was it went out and actually baked the spacecraft in the sun for 6 months before we ever opened it up. We
So
said
any of the high energy contacts you would get would be at a lot of angles from the impacts you would expect from the comet. Right?
yeah, right. That's right. Usually, in general, that's right. Might be unlucky to have one coming directly in,
Yeah.
and there's always that problem. But so far, we haven't had that problem so far. We'll see. So, move ahead here. We've come up with all kinds of unique ways of moving the samples from the air gel. We could use a razor blade, just chop it up. We do that sometimes. We also have computer-controlled micromanipulators which go in and just peck out little triangles of air gel that contain the tracks. This is a millimeter-long piece of air gel. Inside is a very, very tiny track, the entire track. You then can carefully excavate the particles from this piece of air gel, or take this little piece sitting on a fork and put it in, say, a cyclotron light force and look at the fluorescence from X-rays inside of the sample, look at the bulk chemistry. You can map it out, looking for organic rich particles in this little sliver. So you can do some analyses on the entire track, but the track is still enclosed in the air gel because it's so low density in light. Before you chop it up and remove the particles from it. That'll happen just down the road here at JSC. So here we have a little sliver of air gel with 2 tracks in it. I think this is actually two rather large tracks. These are about 5 millimeters long, and each of these has many grains in it. These grains were then removed from the ends of the little tracks here for analysis. And they're mostly all pyroxene, these particular ones. Small though they are, these grains are only maximum grains are about 15-20 microns in size. This particular track, that's still big. You can do a lot with these grains, like this. You can take a little grain that's, say, 10 microns in size. You can slice it up and then send out the slices to different labs to do anything you want, almost. Look at noble gases, some noble gases, and in a rather thick slice. You can do analyses of mineralogy, petrography composition. So you look at the isotopes of particular elements, to give you an idea of the origin history of elements. You can look at the structure of organics, history of carbon, origin of life's just in there as a little deal there, right? The idea is that if comets really are the source of most of the organics in the terrestrial planets, including our bodies, then the building blocks of complex organics should be in comets. And so part of the reason for this mission was to return organic molecules from the comet and see what's really there. There's an amazing amount of things you can do with a single little grain. And every year you can do more and more. So some little rogues gallery of grains now. This particular grain, like many of them, in order to analyze them, we embed it in a special low viscosity epoxy, then slice up the grain like you cut a loaf of bread into 1,000 angstrom thick slices, and then dole out to laboratories. So this is a thin sliced particle. This is in a transmission electron microscope. Okay. So this stuff out here, this is the epoxy surrounding the particle. Here's the thin slice, like a loaf of bread, of one particle. This is a half micron scale bar. This slice is about 700 angstroms thick. Okay. And what we found is that this grain is mostly olivine, which is a magnesium iron silicate, a very simple, very common mineral, probably the most common mineral in the Earth, for instance. One of the most common minerals in the solar system, olivine. Now, we expected to find olivine. What we didn't expect to find were because we thought comets formed far from the sun, and that all materials in the comets formed far from the sun, we thought we'd see lots of low temperature minerals that formed far from the sun, right? Things that were forming with ices. But instead, we're finding rather a lot of minerals which must have formed very close to the sun, unexpectedly, for many people. This particular track, that's called track 25, right? They're all given numbers, right? We pulled grains out along this track. Here's some right here. And this track was a revelation. Here is one grain from this track. It's been embedded in epoxy again, sliced real thin. And these arrows point to different minerals in the track. And the point is, all these minerals are extremely rich in very refractory elements: titanium, aluminum, calcium. It's amazing. And minerals like this are found in meteorites, and these minerals would have formed it at a couple thousand degrees C. Okay, so this mineral cannot have formed far from the sun. It must have formed right up next to the sun. Okay, it's been totally frowned. Very unexpected for most of us. Again, I say minerals like this are found in meteorites. Here's a piece of a meteorite which contains minerals just like this. These little aggregates here. This is about a centimeter across, I think. They're called calcium, aluminum rich inclusions because they're very refractory, or CAIs. And these are thought to be among the earliest materials that formed in the cooling solar nebula as the gas and dust was condensing further. Up close to the sun, where you have high temperatures, you have things that are melting, getting fried, and when they crystallize, you have very high temperature minerals forming. Okay, and when these are dated, they're extremely old. Okay, and we thought they only formed close to the sun. If that's the case, then what are they doing in a comet, which is supposed to form very, very far from the sun? A big mystery by this. One cool thing is that if you look inside of this crystal here, spinel, magnesium, aluminum oxide, inside the spinel at very high magnification, this is now a 25 nanometer scale bar, okay? Grains here, which are titanium, vanadium nitrides. The titanium nitride, in this case a lot of vanadium is in there too. Here's a spectrum here. Nitrogen, titanium, vanadium here. And this particular phase, here's a stability field for this phase, and this shows temperature, and this shows the carbon-oxygen ratio where it's stable. This particular mineral is only stable in a very narrow range of carbon-oxygen, about 1, which is rather a lot of oxygen actually. And temperatures, more than 1,000 degrees C. So pink field is where it's stable. Okay. So peckified minerals that formed, way down here. Serified minerals that formed way up here. Okay, mixed with the low temperature materials. So this is one of the probably the most important single discovery for the mission was these particular high temperature minerals. Okay, and inside of those minerals you find other really weird things. This is a grain, so the same sample. This grain here is a nugget of iron, nickel, ruthenium, platinum, osmium, iridium. Here's a molybdenum tungsten grain up here. How do you get that? So these are extremely very temperatures, but for the most part very high temperatures, noble metals. So it's just a little grain sitting inside of this spinel. This is probably a nebular condensate, but a very high temperature one. But very, very tiny. Again, this is a 20 nanometer scale bar. This is really tiny guy here. Okay. Well, there are other grains that are also high temperature as well. Don't worry about most of this, but this is another part that's been embedded in epoxy and sliced real thin like a loaf of bread. Here's the epoxy again. And here is the grain. This grain is a very iron-rich silicate called phthalate, which is the white here, by the way. And then silica, SiO2, like you see in window glass, like the aerogel, for instance. Okay. But this texture here, these two minerals are together, this sort of texture basically requires that it form through melting. This is an igneous texture, probably. This sort of texture you see in really high temperature minerals, you see in meteorites. It's not what we thought we'd see in a comet. Okay. This particular track is kind of cool. Here's the track, this is the aerogel here. Particle broke apart on entering up at the top here. Grains are all inside the track. And then here are terminal grains. This one's pulled out. It's here. It's embedded in epoxy. It's sliced. then photographed, and here's how it looks again in the electron microscope. This is the epoxy again. Okay. Here is most of the particle is this mineral, which is iron sulfide. Okay. Give me the particle stuff right here. This is again this NGSL3. This is a mineral pyroxene, magnesium silicate, a very common mineral in meteorites. But the stuff here is really cool. This is showing right here. This is extremely porous, extremely fine grained, and this is a little scale bar. Okay, this is 12 micrometers across. These are big crystals of iron sulfide, magnesium silicate. But this stuff in here is extremely fine grained, nanometer-sized crystals all mixed together. And the bulk composition of this is the same as the solar photosphere, the sun. Okay, this sort of stuff we see this is what we thought we'd see in comets. Very fine grained material with a composition like the sun, very rich in low temperature elements, for instance, as well as high temperature ones. Okay. Here's what we thought we'd see, and here it is. But see next to grains which formed very close to the sun from very high temperatures. And so this comet apparently formed materials that themselves formed all across the early solar system. So our model for comet formation is now out the window. Okay, if they really all formed far from the sun, the material that made up the comet came everywhere in the solar system. Not just stuff that formed out where the comet did, but also material that formed farther in, close to the sun, and up next to the sun as well. And it was somehow transported out to where the comet accreted. Okay. And if you take a close look at this fine-grained stuff here, some pretty cool things in here. Here's another picture. This is the image that's showing carbon. It's a map that shows where carbon is, just in one little sliver from this grain. So again, we're back in this fine-grained stuff here, looking at very close at some of this stuff. And again, this is a 1 micron scale bar. There's a 0.2 micron scale bar. Here you have material that's basically pure hydrocarbons. Okay. And this stuff has a very odd concentration of an exotic isotope of nitrogen, nitrogen 15. Okay, very high concentration of that. And to get high concentration of nitrogen 15, which is kind of an exotic isotope of nitrogen, requires very low temperatures. Okay, it's the opposite of what you'd think you'd see next to the sun. This stuff must have formed at the very edge of the solar system, out maybe even in interstellar space. Okay, and it's in a grain that's next to a grain that formed next to the sun. And so this comet has everything in it. It's got material that formed at the very edge of the disk, perhaps even interstellar space, and preserved in hydrocarbons, which never can be heated very much at all, as well as stuff that formed right next to the sun. It's really cool. Look at this. This is just a little diagram. We wondered if we'd get any organics in the samples. We worried that the impact of the particles into the air gel would be so energetic would destroy all the organics. They'd be heated up and just boiled away, right? Or be fried. But it didn't happen. I mean, as you can see here, this grain miraculously preserved lots of very low temperature material, including material that formed at very, very low temperature. And if you look at the organics, there's extremely odd structures. This is a Zane spectrum. This is a X-ray technique for looking at the bonds between carbons and carbons and carbons and oxygens, carbons and hydrogens in minerals. And so when you look at the organics, the Zane spectra tell you roughly what structures you have inside the organics. And so for the first time, they're actually working out the structures of these organics in the comet. These are the actual building blocks of organics on the Earth. So when we wonder how the form organics were in when they arrived at the early Earth, this is what's going on. This is what's happening. This is the form of those organics. It's really cool. We worried we wouldn't get any organics at all in this mission because they couldn't afford to land and collect it properly at low temperature, but it worked anyway. Some materials survived miraculously in the air gel. This is interesting. This is a strange thing. This is another grain. Okay, it's mostly again these magnesium iron silicates. Okay, so again this is another particle. It's been embedded in epoxy. It's been sliced. This is what's left after you sliced a few layers off of the particle, and then it's mapped and analyzed for the isotopes of oxygen. So this grain is called gozen sama, which I'm not sure what that means in Japanese, but it's some kind of food, or what's gozen sama, do you know?
Look at the body.
Okay, so this is this grain's about 10 microns in, 20 microns in size. It's placed in a special instrument for analyzing isotopes in ion probe with a very, very tiny beam. And basically, these holes presents one analysis for the 3 isotopes of oxygen. So here's 2 grains that are side by side in this grain, and here's the analyses from that. And this is plots results for the 3 isotopes of oxygen, 016, 17, 18. This is the ratio of 017 to 016, 18 to 016. Okay. If you look at materials that are on the Earth, your bodies and this desk, and rocks, they always plot along this line somewhere. This shows where the 3 isotopes of oxygen are for terrestrial materials along this line. For most primitive meteorites, they're along this line here, this gray line here. Samples. This is the entire range shown by primitive meteorites. Okay. Well, this one grain here has analyses that plot down here and up here. So the entire range shown by meteorites is in this one grain. You go from here to here. It's just amazing. Okay. And so we have meteorites that sample many asteroids that sample materials all across the early solar system, and it's same range of compositions is shown in one single grain in the comet. Very unusual. Again, it just reflects that the materials in this comet formed from wildly different places in the early solar system. Very unexpected for most of us. This, coming out of time here. Oh, let's go back. This shows the range of analyses, compositions of these magnesium iron silicates. I was talking about olivine. Okay, what about these numbers? Okay. Point is that the range of analyses for particular meteorites is shown here. Here's one meteorite called Murchison. Here's one called Semarcona. Okay. The range for this comet are as wide as all these meteorite types put together. Okay. The analyses for this olivine go all the way from here, a pure magnesium member, all the way here, to pure iron member. Again, reflecting that extremely wide range of formational compositional areas. One last thing I'll show you here. This is kind of cool. Another track. Let's get the part from the right here. Broke apart, made this big bulb here, and then deposited grains here. Here's one grain that was pulled out. Then here it is photographed in a microscope. Then it was put in epoxy and sliced up. And here's how it looks. This is epoxy again. Particle. This is just a polished part of the particle, basically. This is a 2 micron scale bar. This contains 2 minerals, nepheline and iron-rich olivine. And again, this texture, all these wildly elliptical and sinuous mineral grains requires that it's had to have melted for formation. So again, this grain was melted in the nebula. People have asked, comets, they have dust, they have rock, they have water ice, right? Were they ever warm enough in the past where you had water ice melting liquid water and maybe reacting inside with the minerals to form minerals that you might see in your yard in Houston, right? In your clay minerals and carbonates, things that form in wet environments. And the answer is maybe, okay? Although most of the comet appears to be, these minerals appear to be totally dry, here and there are a few grains that suggest there was liquid water in the comet once. They're very rare, but here's a little grain. There's a 100 nanometer scale bar. It's an extremely small grain. And this stuff here is magnesium iron carbonates. This is a calcium carbonate. This is actually calcite, by the way. One of the rare analyses I actually figured out what it was. Okay. And in the Earth, carbonates like this usually form in marine environments, like in the ocean or in lagoons. Occasionally, they can form in igneous from melts, but very rarely. And so when you see a carbonate, calcium carbonate, or magnesium carbonate in meteorites or anywhere else, you usually think, oh, it formed from liquid water, the activity of liquid water reacting with rock. this comet, again, there are a few tiny little rare grains of carbonates here and there. So maybe at some time in the past, there was actually liquid water in this comet. There are wild theories that maybe comets had life inside at one time. Lots of water inside, liquid water, and organics reacting, and animals in there, and who knows what, right? Or maybe all viruses are born in comets, that come to Earth in comets. I think that's wrong, right? Who knows? I don't think so, but maybe there's some evidence now that there was that liquid water in this particular comet. Not too much, just a little bit. Maybe if we'd sampled the next jet over, we would have gotten lots of this stuff. I don't know. Right? So there's tantalizing hints that could be liquid water present in this comet at some time in the past. Okay, I said that the discovery of these high-temperature minerals was the most important result from the mission so far. Another important result, a question you wanted to answer was, are comets like visitors from foreign solar systems, or do they consist entirely of unaltered pre-solar material, grains from stardust, which were never heated up enough in our nebula to mix up and swirl and mix everything else. Our idea of this solar system was that originally it was a cloud of dust and gas, all rising from destroyed stars. Okay, and each of these grains had a different history depending on what kind of star it came from. Okay, and these grains all have different isotopic compositions for elements like magnesium, aluminum, and calcium, and iron, and oxygen. Okay. But today you see the stuff in the solar system, meteorites and Mars and the Earth and the Moon, are all pretty much the same composition for the isotopes. It varies a little bit, but not too much. Okay. So some process must have homogenized all this pre-solar stardust, mixed it up, and when the planets formed, it had been mixed up pretty well already. Okay. But do comets, they formed long enough ago, early enough in our history, perhaps they preserve a whole lot of this stardust totally unaltered. Each grain having a wildly different composition in terms of the isotopes. Okay. So a big question we wanted to answer was, did comets form so long ago that they're totally stardust grains, or mostly stardust grains? Or do they form late enough in the history of the solar system that they basically sample the average composition of the solar nebula? We don't know. So a big early push was look for preserved pre-solar or stardust grains in the captured samples. And at first you couldn't find any at all. And gradually over the last 2 years people found 50 grains. And they're all extremely tiny. This is an impact, a piece of foil that was around one of the aerogel pieces. This is the tear in the aerogel. So a comet grain came in, smacked into the foil next to one of the aerogel pieces, broke a hole in it, and deposited bits of the dust around the hole. And here's a piece of residue. It's a 200 micron scale bar, so it's a really tiny hole. And when they mapped out this piece of residue here, get into these isotopes of oxygen, they found that one little grain here was extremely high in oxygen 16. Very, very strange composition, okay, which you might expect to see in certain kinds of stardust grains. So this little grain here, this little spot, is a reserved pre-solar grain. But all stuff around it is stuff from our own solar nebula. It's been mixed up and homogenized. So this shows you that there are preserved pre-solar grains in this comet, but mostly it's material that formed locally, been mixed up. In fact, the search for this grain showed that here it is. Here's this bit of residue here. Here it is blown up. Now we have a 10 micron scale bar. This little red circle shows where this little piece of the grain is. So it's an extremely small percentage of this whole giant grain. Okay. So by far, the comet is material that formed late enough in our history that material, all the stardust grains have been mixed up already and kind of homogenized. And it sort of lost its memory of its pre-solar ancestors, so to speak. But there are a few grains here and there that are preserved. And so our picture of how comets form has changed a bit. Our picture of the solar system has changed a bit as well, based on this mission. Here's a little cartoon that shows an early solar nebula. The sun has turned on. This is this cloud of dust and gas that's swirling around, which planets will form in the future. Okay. And the sun's turned on, and it has this bipolar outflow of energy. Materials being tossed out, north and south, like this. So materials swirling in, accreting to the early sun. Okay. This material gets fried and ejected out. like this. And you see this in many young stars, it's these bipolar outflows. And one theory, called the X-wind theory, was that you had a very strong magnetic field embedded in this swirling cloud of dust. The protosolar cloud here, the disk had its own magnetic field. And the early sun had a magnetic field. And where these two magnetic fields crisscross right here at the edge of the sun's surface, we had very strong magnetic interconnection and currents formed. And as dust came in, swirled in, this dust got right here where the two magnetic fields crossed, and basically were charged up and fried and ejected out of the whole nebula. And most of that material then got shot out this way. Some of it, the biggest grains, might have been tossed out like cannonballs and landed back out here again. So the idea is Frank Shu's model is that this is how the high temperature stuff in the nebula formed, how the chondrules and these refractory things form was out here at the edge of the sun. The material got melted, heated up, and shot out and landed out here. And that seems to have been what happened, because that's what we see in this comet now. We see material that formed everywhere in this thing, not just out here where the comets were forming, but also material that formed here and here and here and right here, that somehow then got back out to where the comet was assembled. Whether it was shot out like this or worked its way out to this somehow, somehow this was a two-way street. Material was moving in towards the sun, making the sun larger and larger, making the planets. Some material leaked out and almost got out, and it was incorporated into the comets. In this case, this comet is maybe half and half. Stuff that formed out here and stuff that formed in here. The largest segment of it is material from the early solar system. Really exciting. I'll come to this, okay? In your lifetime, our resolution on comets has changed from this, pictures of comets, okay, which are the largest things in the solar system. They're millions of kilometers long, include the tail, right? To this. We now have samples of comet grains in the lab. This is an electron microscope image of one olivine crystal, magnesium iron silicate crystal. This shows rows of atoms. And the change of scale from this to this is 18 orders of magnitude. So we've had a fantastic increase in resolution understanding of comets just in your lifetime. Progress. We have most of the samples haven't been analyzed yet. They're still in the lab. Here's a picture looking in the lab. This is the tray as it was a couple of months ago. We pulled out about I think 1/5 of the cells so far. And our plan is to leave most of them in the tray for our lifetime, and just very gradually pull them out for analysis. And who's this person here? Do you know? So I say what this mission is. The famous guys come to the lab. It's really nice. I think this is my daughter. She's here in the lab too. So, questions? What time is it? 8 o'clock yet?
Yes, a little after 8.
5 more minutes, real quick. Yeah,
Okay.
just a second. Okay.
Yeah, I have a question.
Yes.
You talked about how the comet, when you saw it, the actual pictures of it, was a lot heavily cratered than you thought it would be. Is it possible that could have just happened with interactions in with the asteroid belt inside of Jupiter over the last 30 years?
No, there's no way. There's not enough asteroids to have caused that in just 30 years. However, if you remember, I said these pinnacles, these spires were 100 meters high, right? People who do models of comets, they basically, in their computers, take the comet out beyond Jupiter, bring it in near the sun, heats up a little bit, right? Loses some dust and gas, goes back out again, right? Every pass by the sun, it loses some more dust and gas. And the average comet, they think, loses about 1 meter of ice every close pass by the sun. And so to have spires 100 meters high means this comet must have been by the sun at least 100 times in the past. Okay? And that couldn't have happened if it was orbiting out beyond Jupiter all the time. It could only have happened if it was at an orbit like it has now. Okay? Maybe even closer to the sun. That suggests perhaps this comet has been in and out of the solar system many times in the past. Maybe it's been deflected in and out many, many times. And maybe that will explain why it has so many features that look like impact craters. We don't know. It's like everything else in science. When you step forward, you take 2 steps back sometimes. You thought you understood comets very well. Turns out we don't understand them very well at all. You got a question?
Did you find any diamond crystals?
Not yet. I mean, there should be, if you look at meteorites, primitive meteorites, it's about, how many parts, no, it's less, it's like parts per billion, I think, right? Diamonds? It's less than parts per million to more than parts per billion. Little nanometer-sized diamonds in meteorites, which are pre-solar grains. They formed around, I guess, carbon-rich stars, right? And so some of these pre-solar grains, in meteorites at least, are diamonds. The grain I showed you there was lost during analysis. No one knows what it was. It had too much oxygen to be a diamond. There's probably some kind of a silicate, perhaps, or an oxide. But we're expecting to find diamonds in there, but they'll be very tiny. There are preserved pre-solar grains in meteorites. They're just magically preserved, but they're very low concentration, parts per million, parts per billion abundance in meteorites, some meteorites. And they're very tiny. I mean, if bacteria had engagement rings, these diamonds are the right size for that, okay? That's how small they are in meteorites. They could be even smaller in these Stardust grains. And as lead-in, what I wanted to say was, for 5 minutes, the spacecraft's orbiting the sun like this 3 times on these black loops, okay? It's traveling like this, okay? This little diagram here, this arrow shows the direction that fresh interstellar dust and gas pass through our solar system by. So as our sun is in the galaxy, as the galaxy turns, right, dust and gas, interstellar gas from other stars, sort of pass through our solar system. It's like driving through a rainstorm, right? And since the sun is traveling in the same direction, more or less, as the galaxy spins, this dust and gas always appears to come from pretty much the same direction, this direction, okay? And based on the fluence of these little dust grains of interstellar dust, fresh dust grains, we figured that if we open up our spacecraft and we're traveling in the same direction, we'd expose the back of this collector to this fresh interstellar dust and gas. We might be able to collect some fresh interstellar dust, such as passing through our solar system, today, basically. That was done. We actually flew 2 collectors back to back. One collector for comet stuff, but one collector behind the other one for interstellar dust. And so when the spacecraft is traveling along these purple tracks right here, we're more or less traveling in roughly the same direction as this interstellar dust is traveling. We opened up the collector and just left it out there for a couple of months at a time, and hopefully collected maybe 100 grains of interstellar dust in the back collector. Well, there were 2 trays back to back. The front one for cometary dust, that worked, but the back tray for interstellar dust, fresh interstellar dust, we don't know if that worked or not yet. Okay, and here's the tray now. The lab right now, it's being analyzed. Basically, we're moving from cell to cell and making millions of little in-focus movies looking for tracks. The problem is the cometary grains are small, right? 100 microns, 40 microns, 10 microns in size, right? But the interstellar dust grains are much smaller still. They should be less than 1 micrometer in size, the largest ones, and traveling very, very fast, much faster than the cometary grains are traveling. And so, although we have thousands of impacts across the cometary tray, we expect on this interstellar tray maybe a total of 100 impacts, and the largest grain to be maybe 1 micrometer in size, and the smallest ones much smaller still. That means we'll have less than 1 interstellar grain per piece of aerogel. Okay, so you can spend a lifetime looking through with a microscope to try to find impacts made by these teeny tiny little grains, little bitty tracks in the aerogel. And so to speed things up, we enlisted the help of people around the world, and there are over 23,000 people around the world who are going online every day in their free time. I think some of them are doing this every single day. It's kind of strange, eerie maybe, right? And they look at these movies they put online to look for possible impact features in the aerogel. And this is called Stardust at Home. You can join if you want. It's not too late. We've only scanned through the tray so far. We found about 50 possible candidates so far. Here's what you see. If you go online there, you'll see movies like this. And as you move your tracker up and down, you can focus in and out of the aerogel. And the idea is to see tracks in the aerogel. Very tiny tracks, okay? And here's one here. This is a possible interstellar impact here. This little thing, this is not the particle, this is a hole made by something hitting the aerogel. and the whole track goes from here to there. It's less than 100 microns long. Okay. So this whole field, a piece of aerogel, is one little, 2 micron diameter hole with a 100 micron track behind it. And so 23,000 people are looking at these every day, searching for possible tracks. Find the candidate here. One there somewhere. I think it's actually right there. You see the arrow. But this one. The aerogel is not perfect, right? It's kind of hard to do this. That goes from here to here. Sorry, it goes from here to here. The obvious one here. So right now we're in the process of this week, pulling out the first pieces of aerogel from this interstellar tray, looking for interstellar dust grains. And this is really almost beyond the scope of what we can do right now. I mean, with the Stardust grains, the cometary grains, we can pull them out, cut them up, and do all kinds of analyses. But for grains that are maybe 1 micron in size and smaller, there's almost nothing you can do right now. But the beauty of a sample return mission is, if you can't analyze it now, you just tuck it away for 10, 20 years, and when you can, you pull it out and analyze it then. But you may see results very soon from the first interstellar grains pulled out of the aerogel. It's exciting because although the Stardust grains are sampling material from 4.5 billion years ago, this is stuff that's passing through our solar system today, right? From different stars. So pretty cool. So it's really 2 missions in one. So it's only $100 million per mission, perhaps, right? Okay, that's all I had. Any questions? Yes.
How was their aerogel developed? How did engineers arrive at the density and all they needed?
Yeah, originally it was developed back in the 30s, and it was used for cosmic ray track detectors. But basically, you make it under high pressure, high temperature. You mix material that contains silica with 2 different alcohols and something else. Take it at high pressure, high temperature, and then you basically open the little spigot and then remove the organics at high temperature, and then gradually lower the temperature. So you basically bleed out. So you at high temperature, high pressure, you make this like gel material, right? And then at high pressure, you slowly relieve the pressure, bleed out the organics. They volatilize and come out. You lower temperature very slowly. You're left with this network of silica. It's almost like smoke. What you have are tiny little nanometer-sized bits of aerogel in little fibrous networks that are just barely bonded together. So it's made in high-pressure, high-temperature bonds. And they use it for all kinds of things. It has incredible insulating capabilities. It's like 100 times better than the insulating material in your house, for instance. So aerogel is used to insulate the Martian rovers, to keep electronic boxes warm inside the rovers. They use aerogel now. In Europe, they use aerogel to insulate homes. For, I think it's about a quarter, you can buy a piece of aerogel in Europe this big and put it in the wall of your house. If you're wealthy, you can have your house insulated with aerogel. It's much better than anything you can buy here. You can insulate windows with it. It's also used in fusion, tokamaks, fusion reactors, to confine the fuel. They'll confine the fuel in a little glass microbead with aerogel inside, to then use to confine the tritium, whatever, I guess the hydrogen fuel. So they use it for all kinds of things. There's actually an international aerogel conference every 2 years somewhere to discuss uses of aerogel. And you can make it out of anything. This is silk aerogel. We've got aerogel made out of carbon, seated carbonate aerogel, lithium borate aerogel, alumina aerogel. We're using tantalum aerogel now for materials. So you can make it, anything you can put in a gel form, you can make aerogel. Questions?
All right, let's thank our speaker.